Welcome to this webinar on the role of machine learning in 6G wireless communication networks. This webinar is a part of a series of webinars that are organized by the University of Oulu 6G flagship project on Research Visions series for 6G wireless communication networks. My name is Saad Ali. I'm with Nokia Bell Labs at the University of Oulu, and joining me today are Professor Walid Saad from Virginia Polytechnic University and City at United States, Professor Nandana Rajatheva from University of Oulu, and Daniel Steinbach from InterDigital. This webinar is a deep dive into the white paper on machine learning in 6G wireless communication networks. This white paper was one of the 12 white papers that were written by a group of more than 200 experts from all around the world on various topics of wireless communication networks. This particular white paper had more than 20 experts from all around the world, and it covers topics such as general role of machine learning in wireless communications, machine learning in physical layer, machine learning in MAC layer, and as well as application and higher layers. We also have discussed implementation aspects of the role of implementation aspects of machine learning in wireless communication networks. In today's talk, we will first start with Professor Walid Saad, which he will give a talk on general role of machine learning in wireless communication networks. Now, I'd like to kindly ask Professor Walid Saad to start his presentation.
So the first question we should all ask, why really we want to do this? So the first answer we could immediately say for those who are generally skeptical about machine learning, we're going to say that machine learning will be there for non-communication functions. So you will have autonomous vehicles, drones, all sorts of applications that will use machine learning for issues that are not related to communication. And as such, 6G must at least be able to support those, even if you're not a believer of machine learning for communication. You should be at least aware that there will be learning algorithms operating over your network. Now, the second possible reason is that we want this. I mean, we've been talking about self-organizing networks for a long time, but now we want more of or less something that we could call self-sustaining networks, which are networks that are able to operate with less rigid protocols and that are able to kind of self-optimize, change their configuration, adapt to the networking environment. And of course, there's the eternal need for proactiveness, learning the users or learning the communication medium that has started with 5G and it will continue on with 6G. So there's possibly, you could condense the role of machine learning in 6G into three categories. The first one would be, as I mentioned, this data analytics for proactiveness. It already started in 5G, even someone would argue even before that, where we want to use all this collected data to do some proactive decisions in the network, and that will continue. The second is more on AI-based optimization and control. So the control of the network, the resource allocation of the network, the optimization of cross-layer functions. These will have to benefit or could benefit potentially from machine learning. There has been work before on this, but now it's becoming more and more a reality, and that will be even more the case in the next 5 years or so. And the last or third use case would be more on edge learning and small distributed data, which I'm going to talk a lot about at the end of this talk. So the first use case, I'm going to just present it in one slide. I'm not going to talk too much about it. Most of you, because have worked on this, and I think some of the next following talks will also talk about it. So you will have massive volumes of data in a wireless networks. I'd like to call it like a hurricane of chaos. And machine learning will come into play to make sense of that chaos. And this could come across the network. It could be just user learning, right? Learning virtual reality, behavior of the users, and so on and so forth, as well as learning the physical layer. And there could be a lot of applications there. However, I'm not going to talk too much about this use case today. I'm going to start with use case 2. And in use case 2, the idea is machine learning is not a data analytics tool per se. It is an optimization tool. It is really a tool for self-control or self-optimization of the network. This is kind of, we want to go into a real SON where we really can optimize different functions of the network from multiple access to the physical layer to routing and networking functions. And in some sense, you would again argue why should we do this? Of course, machine learning provides this autonomy, and that's, of course, the bigger picture and the bigger motivation for that. But also, there will be most of the devices in future 6G networks will be AI enabled. So we could use their abilities to the benefit of the communication network. Now, in this use case, of course, ideally you would have data, but because we're looking at an optimization algorithm, you could always have some meaningful result with either synthetic data or numerically, because you're eventually solving an optimization problem. However, in this area, there's a big role for reinforcement learning, but in my opinion, reinforcement learning has some limitations. And to that point, I want to present an example from our recent work, which you would see the problem itself is a very traditional, very concrete problem that we've worked on before, but there is a couple of caveats that come into play when you look at it for future networks. So the idea is to look more at connected autonomy over wireless. So this is an example of this use case too. As you can imagine, the presence of autonomous vehicles, drones, and also the Internet of Things in general has led us to this paradigm of reliability and low latency. So we no longer want to only guarantee high data rates. We also have to have some sort of reliable low latency communication. And in such an ecosystem, you would have to say, okay, if we want to connect these autonomous vehicles and all these autonomous components of a city, you should still have high data rate, right? So navigation, HD maps, and all sorts of surveillance data, that needs terabytes of data, and that kind of looks at the 6G, terahertz, and terabit per second paradigm. We also need low delay, an extremely low delay. So 5G said 1 millisecond, 6G says below that. So we need like near zero delay. We also need to have pervasiveness, and that I'm not going to talk too much about because it's not really relevant for today's talk. But we also need to have reliability, which means you need to sustain low latency for a long period of time. So many people talk about reliability now. The first thing that comes to mind is URLLC, the 3GPP reliability. In that context, it's a bit very well defined. You have short packets uplink. You need to guarantee very low block error rates, and that's what they call reliability. I'm going to try to think beyond that today and a little bit projecting towards 6G and more. So even though I might use the URLLC acronym in some slides, I really don't mean it in the strict 3GPP sense. What do I mean about it? So what I mean about it is first, the prior art, 3GPP onwards, is IoT uplink sensors. I want to look at downlink, autonomous vehicles, drones that are receiving high rate data. It's not necessarily short packet uplink. Second, most of these prior works on URLLC, because they deal with delay, they often assume known models for the traffic. But the problem with latency is no matter how you model it, there's always a component you forget because this is a very large network. You want to model end-to-end latency, and there are so many factors that it's very hard to capture them through MM1 or more elaborate models. So I'm going to remove that assumption. Second, we're going to look at deep reinforcement learning in more detail. We want to see how can deep reinforcement learning work in a URLLC environment, in a reliable low latency. Particularly, it's the R and the L that I care about. The ultra could be there or not, depending on your application. And last but not least, most of the prior URLLC work, they assume that rate doesn't matter. Here we assume you might need some high rate. Of course, it might not, it might not be 7 nines and terabit per second. That might not be that strict, although in 6G you might have that. But we're gonna look at some combination of those. So we can call this like HRLLC, highly reliable low latency communication, if you wanna differentiate from URLLC. So let me take a very simple problem, very traditional problem, downlink OFDMA system. You're serving autonomous vehicles and you want to minimize power in a way to allocate while allocating P and rho. So you have here P and rho, which is the power and the resource blocks to a number of users. But the key is I want to guarantee reliability in the following sense. It's not just block error rate. I want to guarantee that my delay threshold is always below Dmax. So here I have kind of the complementary of the reliability. So, but you could have, you can just reverse it. That's not a problem. So gamma I star is the reliability that I want to guarantee. And this constraint, the rest of the constraints are just rate constraint and feasibility. The resource block are either allocated or not, power is positive. So these are not very important. It's really this constraint. So most URLLC work, they look at uplink, this is downlink, but they usually work very much on this constraint. They try to model it with MM1 queues and so on and so forth. So here we're gonna say, no, we don't know what the model is. We don't know what are the components of the delay. All I know is that I need to guarantee this. This is probabilistic, so it's not on the average, it's probably instantaneous. So you need to look at a statistical value of that. Keep in mind, because it's statistical, because it's not just averaging, we are very sensitive to extreme events. What I mean by extreme events is a deep fade, a surge in traffic, things that you cannot capture and that do not happen very frequently. But when they happen, they're a problem for application like HRLLC and reliable low latency communication. So to handle model free, first we kind of like, I mean, empirically, if you think about it, this reliability constraint is nothing but a counting of packets, right? It's how many packets you have that exceed the delay divided by the total number of packets. So the network itself could learn it actually. He could count these packets. I mean, you could do it offline, you could do it online. We're gonna talk more about that, but you could learn that. So it is very natural to think of reinforcement learning because you don't have a model and you can learn it. Now, the next question is, we have a very large state space that includes packet size, channel, and so on. So we really need deep reinforcement learning. And this is where I mean, when we talk about learning, don't always go just for deep because it's very fashionable and it sounds interesting. Sometimes you don't need it. Sometimes you have a very small state space. You have a problem which needs learning, but doesn't need really deep learning. Here we do need it because we have a very large state space. So we have a framework to work on this. I'm not gonna go through it too much because there's only one feature I'm very interested in. So the framework has a component that reduces the action space, and this is more on optimization. A component that transforms the problem into a more meaningful problem. And all of those, I mean, kind of feedback into my deep RL. And of course, there's the reward function and the users. The reward function comes from the optimization problem I showed before. And of course, then you have the network feedback. So again, this is the reward function. It just comes directly from my optimization problem. And you have a weight that allows you to control the reliability. The nice thing here is we can have some mathematical result. The first result, we could show that if you use this reward, and your algorithm converges, then you guarantee reliability. However, there is a problem here, even in the statement of the theorem, because I say after convergence, which means that if you're slow to converge, that might be okay if you're doing something like network slicing, you're looking at eMBB applications. But if you're really in a reliable low latency regime, you don't want this slow convergence. And you also don't want extreme cases, as I mentioned, like a fade that the deep RL has not seen before to kind of disrupt your algorithm. So how do we solve slow convergence and unreliability in RL, not in wireless? So the solution we propose, particularly for deep RL, is to combine deep RL with GANs. So the idea is kind of very simple, and it says that, well, instead of training the deep RL in an environment that is just synthetic data or just limited data, we said, how about we train it offline, as some people have done before, but in a virtual environment that is essentially composed of real and synthetic data. And we have some access to limited data, and that is always the case in wireless. You don't have full data. And even if you do, you don't have the data you want oftentimes. I mean, here I wanted URLLC, very specific data. It's very hard to find it, right? So you have limited real data. You have synthetic data that you can control, but might not be as realistic. The question we ask, can we have some approach that uses synthetic data, limited real data, to augment the data of the deep RL and generate these extreme events that are realistic, but they don't exist in the real data. And the idea came to use GAN. Why? Because GAN allows you to generate fake data, right? And that's the whole purpose of it. If you Google GAN, the first results come back to this deep fakes, this type of fake celebrity photos. Here, what we wanna generate is actually fake wireless data. I mean, by wireless here, I mean the channel packet size, the input to our problem. But we want that fake wireless data to actually conform to real distribution so that I would be able to actually generate these extreme events and generate them in a way that conforms with the real data, not just like synthetic, not just out of models. So what we did is we looked a little bit at the GAN literature to see if there is something like this, where GAN is not just used to generate data, but to actually use a synthetic and real input. Turns out that yes, back in, I think 2015, Apple had a similar idea, but not related to what we did. The idea was that they wanted to generate figures or photos of eyes looking in different directions. And they had a synthetic generator that can generate photos of different eyes, but cannot change the direction of the eye. What they did is they had unlabeled real images, synthetic images, and what they call the GAN refiner. And they had an architecture for the GAN. I'm not gonna go through it too much today because we have very limited time. But what they did is in this application, they tried to use this refiner, or they proposed this refiner to generate these actually eyes. What we did is something similar, inspired from that. We have synthetic data generated based on models, if you wish, or whatever you want. Keep in mind, I don't assume models in my algorithm, in my paper, in my work, in my formulation. I just use it in the training set. And then you have unlimited real information. For this case, we used packet arrivals and channel information, and actually also packet size, which I forgot to put on the slide. And this is a very limited real data. We found it online. This is data we can control. The refiner allows you to control the generated output to be coming from this distribution, which you can control, but also conforming to your real data. In some sense, I want a celebrity who is bold. And that's a very extreme case. They don't find a lot of bold celebrities or a lot of celebrities with green hair, let's say. So I have some data on green hair celebrities. I can generate photos from synthetic data on celebrities. How can I generate these extreme cases? So by doing this, we call it experience deep RL. The idea is you're gaining experience in an offline environment. So this is offline, does not really interfere with your network. And then you can apply it in the real environment. And you can see, I'm gonna show the simulations. So you can see with the real data set, we use the real data set, as I mentioned, online. We found it online. So we can see first that in terms of the comparison between four things, our proposed experience agent in red, a vanilla deep RL without experience, you can see how much better we are in convergence compared to the vanilla deep RL. If you pre-train with only synthetic data, it's this green, we are also much, much better, particularly in how fast we converge to the final value of the return. And then we compare to the one that is pre-trained with real data, we are quite similar to it, but we're better in the next slide. And this is where it gets interesting. The whole idea of reliable is that there could be some extreme events. And here at epoch 100, we inserted an extreme event, which is a surge in the traffic in the packet arrival. So it increased significantly suddenly. The packet sizes also increased suddenly. You can see that the vanilla deep RL takes so long to actually cope with this. And this black part is really what's bad with existing deep RL. This, you can think about it, current state of the art, this black curve. Even if you train with the real data, this blue curve, it takes so much time for it to actually adapt to this extreme event. Notice the difference with experienced deep RL. We adapt almost immediately. It's a very short transitional period. So this leads to some open questions. So of course, you can improve our algorithm by using more advanced neural networks. So we use just deep Q in some sense. And you can look at multi-agent scenarios. So this is a single agent. And then convergence is more difficult. You have to look at multiple users. That becomes more interesting when looking at large-scale networks. You can also, again, design deep RL architecture with a more interesting backbone, like recurrent neural networks and so on. You can see some of our other works there. And you can have more control on the GAN. So here we proved, I did not show this, we proved that there is some region within which you can really have faithful reconstruction of your real data, but in other regions you can't. So you can have more control on that. And there's a lot of interesting question there. And you can think about this applied to other problems. So this is, you can see, I used a very power control, simple problem, but you can look at it at more complex problems, including imaging, including terahertz, millimeter wave, and things of that sort. So now I'm gonna try to move to use case 3, which is edge AI. I'm gonna give some example there as well. But what is the idea there? Most existing 5G or before work on AI usually relies on a central controller. You send data to a central controller, it does the machine learning, sends it back, or it could be kind of distributed in some sense, like in federated learning. You send the model of the data to a control server, and then that control server sends you back the model. And that's kind of like the current state of art. So it's like 5G, 5G plus, where we're gonna look at federated learning. And then you can think of a future case where you don't send the data at all, and everybody kind of collaborate in a fully distributed manner to share a certain model, and they only share the model, they don't share the data, and they try to learn some, distribution, a channel model, a resource allocation solution, and so on and so forth. In all three of them, you can think of different types of learning, right? It could be supervised, unsupervised, reinforcement learning, and so on and so forth. So this issue is really driven by the idea that in 6G, instead of having a cloud big data, you will have massive data, a lot of data, but it's distributed at devices. It's partially distributed at a large number of devices. And these devices want to make sense of it. They want to do better with it, and in a way to learn a task together without sharing the data. And this brings in the federated learning idea, of course, from Google and others, in general distributed learning, because then you can look at distributed data that is massive and without the central controller, or at least as in federated learning, the central controller just averages the models. It doesn't do much than that. So of course, you can use federated learning to improve communication and to do resource allocation. And because I talked about this in the use case 2, I'm gonna not talk too much about it. But now I'm gonna ask the other question. When you deploy federated learning in a wireless network, how is it affected by wireless? So what are the wireless factors that impact federated learning, and how do they impact it? So this is an area ripe for exploration in both of its phases. So both for using federated learning or distributed learning in general to improve communication functions, or using 6G as a network, designing it to sustain learning functions. But let me start with this idea of basically joint learning and communication together. The idea is the following. If you look at this figure here, if you deploy federated learning over user devices in a cellular network, let's say, there is a base station, and now each device has its own learning algorithm. They will each try to basically learn together a certain task of interest, and they will have weights for their neural network. These weights are shared with the parameter server, which is the base station. The base station aggregates the weights and sends back a global model. And eventually this converges as shown in the FL literature. And we're going to talk a little bit more about convergence. The idea here is that in the learning literature, for them, these links that are in blue and red here are just communication links. They talk that they have limited bandwidth, but that's as far as they go. For us, these links are actually fading links. They have an error probability. They have a wireless channel that dynamically varies. So these weights may arrive in error to the base station, which means this impacts the learning. And think about the interesting angle here. You're looking at how wireless impacts learning. So the learning here, the task that's being learned may not be related at all to wireless. They might be learning a navigation decision, or they might be learning a keyboard input decision. It has nothing to do with communication, but communication is impacting the learning accuracy, which we advocate then for looking at joint wireless learning together. How can I maintain a good wireless transmission, let's say reliable, low latency, high rate? And how can I also maintain accuracy for the federated learning? So the question we ask, and this is a while back now, there has been a lot of work on this, but we started this about a year or more so. So we asked a very simple question. What is the impact of wireless transmission errors and delays on the federated learning performance? And it turns out that you can actually consider, as I already explained this model, a cellular network, uplink and downlink. And then you can look at the following optimization problem. So essentially, you would say that when you're transmitting these weights, they are subject to packet errors. And you can model, of course, the data rate and the channel. I skipped those for time because I think I have only 5 more minutes. So then what you look, you can, again, here, this is a model of the packet error rate. We say that this global model, which in federated learning is only function of the weights of W, is now function of your resource block allocation R, of your power control P, and also of A, which is the fact that whether the packets are received in error or not. And in this paper, we assumed for simplicity that if a packet is received in error, the base station will actually ignore it. You can have, of course, more elaborate model with quantization and things of that sort. So you can now formulate the federated learning training problem, which seeks to minimize a learning accuracy function. So F is an accuracy function for learning. But now we made it function not only of the input to the learning, which is X and Y, but also to the wireless characteristic, which is the association vector, the RB allocation matrix, and the power allocation matrix. So just by looking at the objective function, you see how wireless and federated learning are now intertwined. I'm optimizing them both, basically. I'm trying to improve the training of FL while taking into account the wireless channel characteristic. And this is not very common. And now it's going to become more and more common. And for 6G, this is going to be probably very standard at that time. And of course, we have the delay constraints and things of that sort that come into play in energy. So I'm going to show the results before I conclude. I know I have like 3 or 4 minutes left. So the first result we show through a theorem that the convergence of federated learning, if you have this, if you don't have wireless, this term goes away. The convergence can be bounded with this. If t goes to infinity, a is less than 1, you will actually converge. Unfortunately, when there is wireless, there is an extra term here. This term does not go to 0 if t goes to infinity, and it depends on the wireless characteristics. And again, I mean, this is depending on Q, and Q is basically the error rate, which depends on the fading and so on. I did not show the physical layer model just for the lack of time. So this is a key characterization. It's a start. So you can now say that convergence is affected by wireless and user association and resource allocation and so on. So now you can think of a lot of problems that combine both. How do I optimize resource allocation while being, cognizant of the federated learning performance, vice versa? You can think of all these problems together. And I mean, again, this is just the optimization solution. So we can now look at optimizing a wireless network to serve edge FL. And now I'm going to show a couple of simulation results and then jump into the conclusion for my talk. So you can see, again, compared our algorithm with the baselines, which are classical learning, who are not aware of wireless. We have a much better loss function, which means we have better inference. And we can show an example on the MNIST database as well. Here you can say on top, the proposed approach, does it identify the number correctly or not? On the bottom is the baseline, which is classical federated learning. You can see we have less errors in the identification compared to that. This is a very simple example. It's just good to show, in an illustrative way. So some remarks. So we can, of course, we can ask what can FL do for 6G, and probably some of the others will talk about that. But we can also ask what can 6G do for federated learning. So the answer is we need some sort of reliability in low latency, because you could see errors coming into play, delay, and for conversions coming into play. Data rate may also be needed. So federated learning, even though it doesn't share the data, there could be models that are really large. Some people worked on what they call communication efficient federated learning. They use some compression to reduce the models, but they're still large. So there could be opportunities to look at, for example, terahertz, sustaining some very large federated learning algorithms. So this idea of joint learning and communication is very hot. You have to try to think of problems there. How can I link them together? What is the relationship? Can I design them to be aware of each other? Can I design a learning algorithm aware of the communication system and vice versa? There's a lot of important questions. You can also think of generative models. We've presented a recent work on this, which is among the first to look at that, where you look at, instead of having inference model, you look at GAN models that are distributed. And that's very interesting because you already are seeing a lot of papers on GAN for channel modeling in 5G and things of that sort. Think if the GAN is distributed, how much richer the problem would be. And of course, you could look at beyond federated learning. It's just one algorithm. There are a lot of things to look at there. And if you think about, in general, what's next in AI, I think issues of reliability, low latency are important. This idea of experience is just one. In terms of distributed learning, how accurate can we go if it's in wireless? And also beyond standard learning, what I'd like to call training-free, if you wish, learning, where you can actually be able to generalize. And this is now in the learning literature, they call it generalization or meta-learning in some applications. And that's a very big area to look at, and it's very useful for wireless. The same goes for theoretical foundations. So I could show you that even when dealing with RL, you can prove a couple of things. And there are some, when you look at emerging 6G technologies like OAM modulation, or even holographic MIMO, there's a lot of issues related to the topology of the signal you're transmitting. And this is where there's some topological machine learning algorithms that can come into play. So it's a rich field of application. And I hope I did not go too fast at the end, but I just wanted to finally acknowledge my students, Ali, Mingje, Tengshan, and Christina, who worked a lot on what I said in this presentation. There's a few works for you could check out as an overview, like on 6G, our early paper on that. On AI, also the tutorial we have, FL and self-learning a little bit more recently. Finally, thank you. And again, I'm very happy to share this with this audience.
I'd like to thank Professor Saad for this interesting talk on especially very futuristic and novel topics such as experience, deep RL, GANs, and federated learning. Unfortunately, Professor Saad will not be available for the Q&A, and we will try to answer the questions directed to him with the other panelists.
Yeah, I'm sorry for that, just because it's our morning and we have several meetings, so I'm sorry.
Yeah, thank you very much.
All right, bye.
Bye. So next we will move to Professor Rajatheva, where he will discuss the machine learning in physical and MAC layer. Please start sharing your screen and start your presentation.
I think you can see my screen. So the idea is that I discuss a little bit about machine learning on physical and MAC layers. So the motivation, I think Professor Walid also mentioned earlier, why we are using machine learning. And as you can see, mostly if you consider these 5G and beyond systems, these are considered quite complex, and there are many interconnected components that we need to design and optimize. So the idea is therefore that when we use machine learning methods, which are data-driven, then these can sort of complement traditional model-driven algorithms. So this is the essential, let's say, drive towards that. And of course, we identify a couple of things as pointed out here. One is that of deficiencies in our traditional modeling. So if you look at this traditional model, means communication theoretic or information theoretic, they are optimal when the underlying things are accurate, right? So if we have, let's say, complicated or complex environment where you don't know the channel properties, so when you have hardware impairments or other things, synchronization, etc., then we cannot capture these in accurate models. So in that sense, then the learning capability of machine learning can be utilized in these scenarios. So using a data-driven approach and try to learn these complex system properties. So one is the modeling deficiencies. The other one is this algorithm deficiencies, where we have highly complex algorithms, especially if you are familiar with optimization. These are difficult to run actually in real time. So this so this data-driven approaches, therefore, in that case, could be more useful in especially latency critical scenarios, which I think Professor Walid also alluded to. And if you consider joint optimization of so many blocks in a communication system, that is a little bit challenging. So those are the reasons why we expect machine learning to do well. Of course, these are the things that are, as I show here, still under research, right? So none of these are yet, let us say, in practical applications. So for example, end-to-end learning in communication systems is one direction. And then channel decoding, as you know, we have to use sophisticated channel decoding algorithms. For example, for polar decoding and LDPC decoding, those are the ones that are used in 5G. So the question is, what will happen then after that? And then importantly, one very important aspect is this channel estimation. And of course, then associated with that is detection. So these are the physical layer topics. And then you have the resource allocation in communication systems, which is like the MAC layer problem that we consider. So if you consider this end-to-end learning, looking at the first topic, sorry. Okay. Autoencoder based end-to-end learning, we have in the conventional communication systems, we have quite a lot of connected blocks, as we are familiar with. And this individual optimization may not achieve as we expect. And that is what we normally do. We optimize our transmitter side and the receiver side separately. So, and that of course may not be the optimal thing to do. So where you have much higher processing complexity. So the idea of this end-to-end learning is to consider this together, instead of having what we call artificial block structure, and try to learn to minimize the end-to-end message and to minimize this reconstruction error. So it's sort of therefore combined approach. So in this case, this is how we normally see conventional communication system model on the top of left-hand side. And then we have the equivalent encoder implementation, which can be trained offline based on the models that we have. And then when it is used online for actual signal reconstruction. Obviously, we need to use the received signal from the channel, and the transmitter side will follow this autoencoder formulation, and then it is transmitted to channel, which is of course not under our control, and then the receiver side also, then it is based on our training model. So what we can show is that, as seen in these graphs in the right-hand side, the error rate or bit error rate performance for BPSK, QPSK for let us say short block lengths are quite good as opposed to traditional standard our bit error rate simulations. So this is one thing. And then of course this was a simple exercise in that sense. This can be extended assuming you have a flat fading channel, and some of those results actually implementations over the AI is shown here, where you can come up with, let us say, reasonable results. So this is still, let's say, very basic kind of development. So we need to look at, let us say, as you know very well, in actual communication systems, you have much higher, much bigger constellation models in QAM, 256, 512, 1024. Those are things that still need to be verified. So, and then extending this to model-free scenario when the channel response is quite unknown to us. So where you can use this GAN type of network to implement these channel effects and to come up with this gradient back propagation scenario using that. So it overcomes these neural network based autoencoders where you need a proper channel model to train the system. So these are then the extensions to this earlier autoencoder based system. So moving on, one critical thing is in physical AI is channel decoding. And why this is important when we consider this machine learning based approaches is that it normally gives to what we call curse of dimensionality, because you have block length, let us say 100 bits. Then if you consider all possible combinations, even if it is binary, it is 2 to the 100. So this is fairly challenging. So what is shown is that if you have what we call structured code words, then without going into this kind of higher dimensionality issue, much better performance can be obtained using some structure. For example, this Tanner graph, if you have that kind of structure, then that can be used for training. And in that case, without having an exponential number of code words, you can come up with reasonably accurate bit error rate simulation. And you can see here bit error rates for different this BCH codes. So this is one avenue to consider rather than considering this challenge of having a block length which gives rise to this exponential type of data scenario that is needed in machine learning. And then we also have the other important aspect, of course, channel estimation and detection. Remember, I started off with end-to-end and then channel decoding. So this is a different block, and then estimation and detection is, of course, another block. So these are different possibilities that we have to think. And in the case of this estimation and detection, of course, you need to, this is practically what is needed in any kind of wireless receiver. You need to estimate the channel, equalize, and come up with the detection, and then to be followed by the decoding. So we need to think of how to consider these different blocks and to see whether we can come up with better processing. For example, in this channel estimation, we can use the networks that are used in image processing and this computer vision. For example, what is shown on the left-hand side bottom, you can see pilot symbols can give some indication of what has to be done. Based on that, this super resolution network will fill the blocks, and then this image restoration network can come up with the channel response, basically using interpolation and noise suppression. So, of course, when you look at the graph, this is on the right-hand side, the ideal MMSE estimator still performs pretty well, but then depending on the noise situation and the training that is done under what signal to noise ratio, you can come up with reasonably accurate channel estimate. So this is one thing. And then the other thing is this joint channel estimation and detection. So there are also, what we can show is you can come up with both estimation and detection together. And this is important, especially when we consider, let us say, a smaller number of training pilots. And as you know, in OFDM, we use cyclic prefix. So when things are not, let us say, in the proper order, and especially when you have clip-in noise, so this kind of network can be used, and you can achieve reasonably accurate results. So this is one thing that we have to keep in mind. When everything is known, of course, you have, we can say the communication or information theoretic algorithm perform better, but when things are, then when we have uncertainties, like training pilots or lack of prefix, or especially you have other type of noise, because our noise normally, what we consider is additive white Gaussian noise. But when we have some non-linearities, then our models do not capture everything into account. So where machine learning can come into play. And then, of course, one thing that is useful is, and in the cases that we have considered earlier, you need to do a lot of offline training, which is, of course, one can say computationally intensive. And it has also different when it comes to the real channel scenario. So one algorithm that was discussed is what we call this complex learning machine, extreme learning machine, where you have a simple machine learning algorithm and which can provide better channel estimation performance. So that is something that is fairly important, especially when we consider these real world channel conditions. And finally, to conclude, we look at briefly about the McClayer issues, resource allocation. So let us look into this a little bit. So resource management is fairly important for improved performance and efficiency. And as anybody who is familiar with resource allocation methods always use CVX optimization tool. And it involves fairly complicated processing. And normally, therefore, is not practically done in real life, right? So, and this is one place where machine learning algorithms can be fairly useful, because it can reduce this complexity, processing complexity, and we can do this resource allocation task fairly straightforward manner using machine learning. So examples, several examples mentioned here: deep learning based massive MIMO beam forming optimization. And then, of course, this new direction cell-free massive MIMO, where also we can consider power control methods and this joint beam forming and power control. So potential research directions in this area, therefore, as Professor Walid mentioned too, this reinforcement learning frameworks and this transfer learning to come up with better resource management with minimal supervision. So some examples for this beamforming optimization, where the deep learning model learns and predicts these beamforming vectors at the base station. So for example, you can see here, it is through this online phase during the coherence interval, you come up with the beamforming, and then you can use it for, originally it is using this all the omnidirectional beam and the other beams. And then once it is trained, then it can use this reception with omni beam, which is optimized to that. So this kind of system is more useful in that way. And then further, you can use convolutional neural network. And to consider all this together, especially when we have channel information not perfect, right? So this is something that runs through this physical layer and MAC layer when we don't have information properly, when we have lack of information, where you can do this deep learning approaches and machine learning approaches. In this case, the second one shows joint optimization, beamforming, power control, and interference coordination. And this is traditionally, people who are familiar with optimization, is non-convex. So it's fairly complicated because you have to then simplify, reduce it to a convex situation, which is then not giving the optimal solution. So, and this cell-free massive MIMO, therefore, is a new research area, but then you have a lot of, let us say, user positions and then access points. So then this is, again, fairly complicated processing. Of course, one can argue that this centralized processor can do this, but if you consider deep learning, this is much more amenable, especially considering different channel statistics and user positions. So this is where another, let's say, possibility for deep learning. Okay, so finally, I think we can look at these different references. I spent 1 minute here just to show. So this Oshia and Hoydis started this end-to-end direction, and then you can also see this model-free end-to-end, and then channel estimation, as well as this extreme learning reference 12, and then the MAC layer algorithm references. So feel free to have a look at this and see how these things are developed. So basically, that's all I want to discuss. Thank you.
Thank you, Professor Rajatheva. It was a really interesting talk on physical and MAC layer aspects, and a lot of topics that are of interest for, I guess, both academia and industry. Next, we will move to our third presentation. Mr. Steinbach from InterDigital will discuss implementation aspects of these machine learning methods, especially in physical layer.
Oh, thank you, Saad. Let me just get the slide presentation. Yeah, my focus is actually a good follow-up to the two previous presentations, because this is more the implementation aspects of it. That we have, we have a lot of theory, and there's of course a lot of promise with machine learning and how it can adapt and how we can use it in 5G and 6G. And the questions are, how do we go through the development cycle, and how do we incorporate machine learning in an actual, platform on a cell phone? So I work with InterDigital, and there are just a couple slides real quick about InterDigital. I won't go over everything in detail. It's more about the technical things, but we're more a research development company all through Europe and the United States here. And we do a lot of work with developing new standards and solutions, and trying to push the envelope as far as technology goes on new wireless communication frontiers. And so in the introduction here, so we have machine learning, And as we talked about in the previous ones, there's, different favors. We talked about, federated learning and generative adversarial network. And we basically can divide that machine learning into supervised and unsupervised learning. So while we have, power and cost and size are always considerations in implementing neural networks, they're even more important, when you get down to a cell phone, because a cell phone, everything is, battery life and speed and so on, and physically putting in the cell phone, and even, network-based, machine learning. It's still, very important that we reduce, power, and that we are able to converge and in a reasonable amount of time and train the networks, because we only have so much time to adapt to a given situation in a network, because then the situation can change, as we saw. So there are several different stages, and I'm going to take us through simulation, prototyping, and then implementation in an actual product. And as we go through, we go more from a software-centric side to a hardware-centric side. And so we have to take all these things into account. In addition, also the performance and how well and it's going to adapt, and what kind of information needs to feed into the neural network, what kind of outputs we're looking to generate, what the cost function is, and how it's going to be implemented. And as we all know, with machine learning, a lot is dependent upon the topology of the network, how many convolutional layers we have, how much pre-filtering we have, how many fully connected layers we have, the number of nodes, and so on, and our activation functions, cost functions, and those are all things that in practice are actually very difficult to get right. I mean, there's no optimal solution, but to get to where we have a very good solution. And so what we really want to do is we want to train our network, typically in simulation in the prototype phase. And by the time we get to a product phase, we're not going to be able to vary the network as much. And we'll get into that in a bit of detail. So, and we'll talk a little bit about simulation stage. And, as we know, a lot of times we simulate either in a C++ environment or a MATLAB type environment, and we use various channel models. And one key thing is, if we're testing a receiver, we build a generic channel estimator, for example, and then we see how well does it work with a certain channel model. The problem is, if we train a neural network with just a few specific channel models, it learns to adapt to those specific channel models very well, but it may be very specific to those channel models. So a big part of it, the training, is to vary the channel models and make sure that it will work over a wide variety of conditions. So whichever aspect of the receiver chain we're trying to implement in a neural network, we have to make sure that that neural network doesn't work just for 2 or 3 channel models that are in our simulation, and then we get to a real world example and it falls apart. So there's several different ways of implementing these artificial neural networks. And there've been some papers about even simulating the entire receiver chain from input to output. But quite frankly, for 5G packet size and so on, I think that's pretty far off. What we're really looking to do is just to augment or to just implement just certain blocks in the receiver, just in the artificial neural network. So, as I talked about, the topology of the neural network is very important, and the termination of that topology is a very, very time-consuming task, because if you're going to try more layers, or you're going to try different number of nodes or different types of filtering layers, or let's feed in, this input or that output, or we derotate, these pilot symbols first and then put them in. Each one of those is a different simulation, and each simulation you want to have multiple runs. And when you're running, even if you're running on and offloading it onto things like graphics processing units, GPUs, these NVIDIA cards tend to do neural nets very, very well, and much faster than a regular CPU. You're still talking about hours and hours for, doing a series of simulations. So, that's a, concern. So even though simulations obviously don't need to run real time, they need to run in a reasonable amount of time so that you can try all these different scenarios. And if you just want to try, let's say, several different activation functions and several different numbers of layers, when you start multiplying out the number of combinations, that becomes, very, very, very large task. And you need a lot of simulation power, and you need a lot of, time just to do this. And it's something that probably needs to be done way before you ever, get to a physical platform. So now, a lot of times training on ANN, as I said, we're going to use many different channel models, and we'll have a Monte Carlo type simulation where we have different random seeds, and it can take relatively a few hours to run, each simulation, because it's generating so much data. So the quality and diversity of the channel models becomes a real important factor in how well that neural network will train. And one of the the major tasks we said is to identify all the structures and features of the neural network, the optimization functions, the activation functions, the cost functions, even to decide what are the inputs that we're going to use. Theoretically, of course, neural network can just learn from, just give it all your input data, all your raw IQ samples, and tell it, you want to get this output. But in the real world, with large packet sizes, that will never converge. So you have to be a little bit smart about how we, get these things to converge, and try with smaller networks and smaller packet sizes first, and then progressively build up, so that we have something that's practical and will be able to, process 5G packet sizes. And so, what we talked about is, some of the, inputs to the ANN, and there's, channel estimator data, there's, the FFT output, pilot symbols, and custom filter data. And just like in video processing, there are convolutional neural networks that are used to reduce the data size, and so that, kilobytes become hundreds of bytes, so that the neural network can actually, process it and be able to converge. And so you may need to have separate filtering functions, but maybe not necessarily convolutional functions, which work on, let's say, video processing, but other functions that will, reduce the data set for a neural network. And so these, gradient descent algorithms, they can be run, we're trying to optimize the system. So, bit error rate is one of the, key points of interest, one of the KPIs that we're going to take into account. Trying to increase the signal to interference ratio. That's also, a big output that we put in the cost function. And then, of course, just cyclic redundancy check is did we properly decode or not, the packet. But only using CRC, whether you decode or not, you'll never be able to get it to converge. So you have to have things that will give you a proper, gradient, so that you can take the derivative of it and then be able to, optimize your weights throughout your network. And, finding, as I said, just to summarize, finding that proper configuration of that neural network that's going to be applicable for, a channel estimator or a decoder or whatever algorithm we're trying to implement or augment in a neural network. It's a fairly sizable task to try to figure out what's the optimal number of nodes. Too many nodes that just, increase your hardware, hurt your convergence time. Too little, it may give you poor performance. So there are a lot of trade-offs here in this in this development cycle. So after simulation, typically we'll have a prototype, and just we show a couple pictures of a couple platforms we had worked on, in our lab. And a lot of these times, these FPGA platforms with phased array antennas can, run real time, or at least 1/2 a quarter speed of real time sampling rate. And we'll be able to try this out in real world scenarios. And the real big advantage of having a physical platform, especially as far as training neural network is that you can train in a more diverse number of environments than you can, because you're not limited to just specific channel models, but you can try to train it to real world samples. So some examples, you might have rural or urban environments, or even indoor environments, and then the speed of which the UE is relative to the G node B, and weather conditions are all things that come into play. So again, you're going to go to an FPGA type environment here, but the FPGA environment, of course, gives you some more constraints that you didn't have in your simulation. And the good thing is you can run faster, you can run the real world environment, but you're also limited. And the other part of the problem that you see quite a bit in the literature is you may train in one specific environment. You may train in an indoor environment and have the network converge and perform very well. Now you go outside and you have to retrain it. And there are a lot of different methodologies to try to remember or not forget previous training. But that's also a factor, is that you want to be able to train the neural network, but you want to be able to train it in different environments and not forget your previous environment while you're training the next one. So there are different things to update how fast we update training weights, and to lock down certain parts of the network and so on, that may help in these situations. And so this is talking a little bit about how well, companies such as Xilinx and Altera has their own hardware, that they're pre-existing IP cores now that implement a deep neural network. And for example, Xilinx, which we're using, they have a deep learning processing unit. They abbreviate DPU. There's a diagram on the right, and it's basically a hardware block that can be synthesized in an FPGA, and it allows the user to allocate resources, DSP slices, digital signal processing slices, block RAM, ultra RAM, and convolutional architecture, just to into the FPGA in order to implement a neural network. So that one nice thing is that a lot of the hardware manufacturers are already looking to assist in aiding neural networks. So you don't have to code individual individual processing nodes from scratch in RTL. There are a lot of blocks that we can use, and there are even custom specific chips. Xilinx Versal is one of those chips as well, and they have 400 inference engines. They're built into the FPGA, along with other programmable FPGA type functions, and so that'll allow a lot more flexibility and speed in the design. And so the goal is now to take the high level topology that we took from simulation, and then now we want to port it over to the RTL and into an FPGA without without starting from scratch. So there's quite a few frameworks out there, and one I haven't specifically used it myself, but just it was interesting reading about it, called DNN Weaver, and it allows a framework that was defined in simulation to be taken to RTL, and then you can generate your own Verilog code from that. So now there are nice ways to take our configured neural network, and we can port it over to an actual physical implementation. And so now there's also certain optimization techniques for the neural network. As we said, size and processing power and is very important considerations. So there have been some papers that said, if you reduce the number of bits in a fixed point multipliers from 32 to 16, you'd say, well, you're going to have half the number of bits. You're going to drastically reduce your performance. But you find out that if you have enough bits, that you only have a very small performance loss, but only 1/8 of the total power and die area is used, which is, real significant, savings. So the question is, how many bits can you use and still have acceptable performance? And at some point, you start seeing a sharp drop off as you reduce the number of bits where you don't have it. But there have been some papers where even quantization to 8 bits can result in very little inference loss, but yet, again, drastically reduce the footprint and the power, power utilization. And there are also some papers that talk about zeroing out weights. A lot of times in our network, some of the weights are very close to 0. And if you simply make those weights 0, then those nodes can be completely eliminated from the network. And there's, of course, a slight loss in performance, but an acceptable loss. So by reducing the number of bits and pruning, close to 0 weights, there are a lot of savings that can be used where you can drastically reduce the power requirements that are going to be necessary if we go to a physical implementation. And so now the assumption is that once we defined our network, we just defined our topology, how many nodes there are and how many connected layers in each node and so on. I mean, how many nodes in each layer. And then the ultimate design is the design goal is to take it from an FPGA to an ASIC. And that brings us to our product phase. And so the final product phase with an artificial neural network would be, we would have to put, strict limits on the number of nodes, layers, and bits, just as, we talked about. And at this point, it wouldn't be likely that this, that in a final product phase, that it would be very flexible at all. So we would assume that during the simulation and prototype phases, we would have decided upon the topology of our neural network. And then that would be pretty much fixed and unchanging because we're going to go to an ASIC. However, of course, we want the thing to be able to still, adapt a little bit and be updated. So, things like, weights and even possibly certain activation function type implementation can be implemented either in software or in RAM, so that we can update, cell phone, dynamically, with an update and with a download. But we do figure at that point, once we go to an ASIC, that the number of layers, nodes, and probably activation loss functions probably cannot be changed that readily, unless we parameterize the activation functions, something to that effect. But the basic functions probably can't be changed. So, this was just a very high level overview of some of the design considerations that we have, going from our simulation, prototype, and product phase of developing an artificial neural network and trying to incorporate these things into a product. So I think that's all I have. Thank you.
Thank you, Dan, for this for these insights on the implementation aspects of machine learning in wireless communications. Of course, that's very important because at the end of the day, we have to implement these on real devices. So now we will move to the questions and answers. I like to kindly ask Professor Rajatheva and Mr. Steinbach to open the questions and answers. I will read those and try to find the person that is interested or most suited for answering these questions. Of course, some of these questions are targeted for a specific panelist. So let's see how it goes. So the first question is that, what are the verification methods for AI ML, and do we use the same traditional KPIs as we use in traditional methods for them as well? How do we really judge an ML technique is doing well in real time? I guess, Nandana, would you like to take that one?
Yeah, sure. Well, we have to use traditional KPIs, of course, right? So for example, let us say that you are looking at a bit error rate simulation. So you need to use that. But in addition to that, then there can be something like relevant to that particular scenario. We can define some figure of merit. So there then can be, in terms of latency or complexity, specific to the machine learning solution. But as we know, I mean, this traditional KPI must be satisfied, right? Otherwise, we cannot say we can deliver the same same quality of service or quality of experience. So you have to use that, but in addition to that, especially if we consider real time, then we have to come up with things that are specific to the particular case, I think. Yeah.
Okay.
Maybe Daniel has some idea because it says real time. So.
Yeah, I think, even, talked a little bit about that in the presentation, that sure, that, if you only look at, packet receiving success or not success, that's not enough to converge. But yeah, things like traditional KPIs such as, bit error rate and estimates of signal to interference noise ratio, I think are very good benchmarks and give you, a proper gradient that will allow you to, iteratively update your weights in your network and then converge. Because ultimately, what do we want? If you're looking at a decoder algorithm, if you're looking at a channel estimation algorithm, you want it, well, how well is it working? And so you always, I think, have to go back to your traditional KPIs. So, I don't know if there are any other ones that in research that people have created ones that are more specific to just neural networks, but I don't really know. I mean, I don't really know of any. Thanks.
Okay, thank you very much. So the next question is related to federated learning. So the question is how is FL model convergence measured? So I guess Professor Saad has left, and I will try to answer this question. Of course, in federated learning, the entire idea is that we have the global model, and then we use these local models that have trained their models to send their models to the server and average them using these federated averaging algorithms to improve the performance. Of course, the measurement of how this process is performing is just simply if the global model that has been generated after federated averaging performs better than the previous model. I guess that would be sufficient enough for us to know that if the federated learning process has worked well. Do you guys have any comments on that as well?
No, I think that's fine.
Okay. So thanks. So the next question was targeted for Professor Saad, but he has left. So the question is, how can OT contribute to FL? So OT, I guess it means operational technology. And do you guys have answer for this question, or should we try to kind of ask it later from Professor Saad himself?
Yeah, better, I think.
Yeah. Okay. There's another question on the role of machine learning with IRS. How can we use machine learning in IRS-aided communications? So
yeah, so whether it is IRS or otherwise, I mean the techniques that we have discussed under physical layer or MAC layer, they should still apply, right? So the question is then how you appropriately formulate the problem. In the case of IRS, of course, you have this issue of phases in the reflector, so the reconfigurable surface. But then the channel estimation issue still is there, or resource allocation still is there, right? So those things, of course, are under research right now. So similar methods should apply, of course.
Okay, thank you for answering that questions. And the next one is, what are the real success stories of AI ML in the wireless domain?
Well, I mean, when people say real success, I don't know if there's any physical cell phone that has that people are using on a commercial basis at this point that has you know, an actual active neural network in there. I mean, not that I know of. I mean, I think this is still a very, you know, a very new area. And I mean, there are quite a few papers out there, you know, where people did anything from, you know, prototyping platforms and simulations where, you know, various aspects. I've even seen where they tried to model the entire processing chain, although it was actually a fairly small packet size using a relatively simple encoder. But I think, you know, as far as I don't know what you know, real success stories. You know, they were in certain cases with general estimators, they were able to get you know, better performance, at least in certain scenarios, you know, according to these papers and so on. But I don't think there's any real physical product out there ready that you know, we're going to say outperforms a traditional you know, cell phone in that regard, or you know, in the network. And I'm not that familiar with, you know, on the network side, how much some of the network providers are using AI. And I know there's research in that, but I don't know to what extent anything's been, you know, fully implemented at this point. So there's been, you know, a lot of success in terms of, you know, small scale type, you know, research where we saw, you know, very positive, you know, impact on performance. But I don't think there's anything in terms of, you know, that's actually implemented out there in a live network at this point. And I don't know, I mean, it could be that something has changed recently. I mean, it's a very fast moving area, but at least to my knowledge.
I think some beamforming in the base stations have been maybe implemented to my understanding. So, but maybe not like really widely applied.
Okay, thank you. So we will go to the next question. This is targeted for Professor Rajatheva. The question is about the use of deep learning in channel decoding for next generation wireless communication systems. What is the best DNN architecture that you think is more adequate to consider for devising new decoding algorithms? Do you think that recurrent neural networks will be more suitable than other architectures?
Well, whether RNN is more suitable or not, I think it's difficult to say. However, to consider the architecture, it has to consider, like when I was presenting, I mentioned, like if you consider this dimensionality issue, if you have, let's say, 100 bits, if you have to train the neural network for all those possible combinations, then that is not good. So the question is then, can you come up with or utilize the network so that it uses the structure of the code, if that can be utilized successfully. So those references maybe he can check, and I think those are the ones that would be more suitable, where we somehow do not need to go into huge complexity in terms of, you know, training, right? Otherwise, this is impossible task. So very likely then the network should be able to capture the structure of the code. If that can be done, then you can make it sort of independent of this, let's say, block length. So that type of architecture would be more suitable. So that's how one has to look at it, I think.
Okay, thank you very much. So I guess this question, I guess Daniel would be the best to answer this question. ITU has established a standard last year for the cost-effective integration of machine learning into 5G and future networks. How do you see that affecting 5G new radio specifications and reflections to 6G research?
Well, I can't say that, you know, I mean, we have a lot of people in our company that are more, you know, experts in, you know, the standards than I am. But I know that, you know, just from having talked to them, that it's being taken into account in terms of, you know, how do you structure you know, the standards so that machine learning can be, you know, can be incorporated at a future date. But in general, I mean, I'm more familiar with, let's say, you know, like 3GPP standards, and you know what they're specifying typically is they're not specifying the implementation. They're just specifying, you know, the structure. So I think as machine learning becomes more important, and especially, I think more, let's say, on the network side. And again, I can't say I'm the big expert, but especially, especially like in federated learning, as is presented, you're going to have standard ways of reporting and collecting all this information. So to the extent that it would be necessary that the data would be presented, and could be even that there's certain information that the network wants to receive from the cell phones that's required to help that's helped to help a neural network converge. And I think if those things are necessary, that would be incorporated into the standards. But I don't know, I'm not, like I said, I don't want to, speak about something that I'm not really, too much of an expert. But I know these things, are taken into account, that, what information would need to be presented to the network from, let's say, all the UEs and collectively, aggregated, so that you can do something like a federated learning type machine learning algorithm. So there's no doubt that machine learning in wireless is getting a lot of attention, and where it's necessary to have some implementation aspects in the standards, I expect that to be in there.
Okay, thank you very much. So the next question is about security. What do you think of security? Does ML increase the overall threat landscape? The federated learning is more prone to security vulnerabilities. Well, maybe I can try to answer this question. So, of course, security is a very important aspect of any communication system and any other computer areas. But I'm not sure if we can say that ML will increase the overall threat landscape, but ML will be heavily used to combating security. So machine learning methods have shown that they are capable of finding attacks, finding anomalies in the network, and they will be heavily used in security aspects. But on the other hand, when we have a system like federated learning, of course, there can be security vulnerabilities, like, for example, a client that is sending a locally trained model to the server for federated averaging process might be a malicious unit that is sending a wrong model, or a model that will just have a negative effect on the entire learning process. So I guess those are the issues that should be taken very seriously. And but the overall conclusion is that machine learning will heavily help wireless networks for combating security. So I will move to the next questions. Do you have any comments on that, Nandana or Daniel?
Wait, pardon me?
I wanted to ask if you have any comments on the security aspects.
Oh, just, well, I know, in general, I mean, there's two different things to separate. One, the security aspect, and I'm not really sure what aspect of security you're talking about. There's an encryption protocol, right, which is lower layers, and then there's the transmission protocol. So as far as it goes, it doesn't need that. If federated learning doesn't necessarily need to have all the decrypted data in order to perform the processing. It depends what you're looking for. It's treating an encrypted packet the same as it would treat one that's not encrypted. So I don't think, in terms of I assume when they said security, the privacy of information being sent over the network. If it's encrypted at one end and decrypted at the other end, it doesn't necessarily need to be decrypted in order to perform the federated learning. It depends, what you're specifically going for. So I don't think there's compromise to the security of a system, because of that.
Okay, so we are running out of time, so we will answer one more question. This one is for Daniel. Any views about using FPGA GPU as a coprocessor for dealing neural networks rather than ASIC for machine learning do it adds more reliability along with flexibility from ML point of view?
Well, without a doubt. I mean, now, I mean, GPUs have almost become like, the standard for, running, neural networks and deep neural networks and machine learning. And the great thing about them is they're so flexible and also, relatively cheap. And, so nearly everything, like I said, in the simulation phase, you're probably going to be running on, a GPU to get any kind of reasonable performance at all. And I mean, you get, even I've seen 100-fold increase, running it on a GPU as opposed to the regular CPU. So there's no doubt if you're deciding on what type of neural network in your early phases, you almost definitely want to do that in GPU, and then there are going to be more limitations if you implement it on an FPGA as opposed to GPU, less flexibility. So as we get from the software implementation down to the hardware implementation, there's always loss of flexibility, but of course you reduce the power and time. So when we talked about an ASIC, we're really talking about the final product phase. But even in, obviously in a UE, but even in a base station, you always want to, reduce the power consumption, reduce the footprint, reduce the hardware. And the only way to really do that is to go to a physical implementation on an ASIC. There's no way you're ever going to be as energy and efficient in an FPGA or GPU as you will be on an ASIC. But of course, with a GPU, you always be far more flexible. So it really depends, what stage of development you are. And as I said, as you progress through the stages of development, you're going to trade flexibility off for, reduction in power.
Okay, thank you very much. So this is the end of Q&A, and there are a few final words that I will share my screen, and we will continue our webinar series, and registration is open for the next 2 6G Research Vision webinars. Edge Intelligence, that will be on 21st of October, and security and trust aspects will be at 28th of October. So please fill in the feedback, online feedback form that we will email you in a short time. And we are using these hashtags when we are discussing our research and 6G, please use them as well. We will continue the discussions. Please stay tuned. Follow our activities in 6gchannel.com. We will also, in a few days, publish a 6G Waves magazine, where we will be discussing a lot of technical topics as well as research directions. Topics such as IRS and machine learning will be discussed in details in there as well. So please stay tuned. And thank you very much. I'd like to thank our panelists, Professor Saad, Professor Rajatheva, and Mr. Steinbach for joining this. And I'd like to thank you all, the attendees, for listening to these talks. I hope you enjoyed this talk and have a good day. Bye.